everybody, and welcome to Scaling the Security Researcher to Eliminate Open Source Security Vulnerabilities Once and for All. My name is Jonathan Leitschuh. I'm a software engineer and software security researcher. I am a GitHub star and GitHub security ambassador, and I'm also the first ever Dan Kaminsky Fellow at Human Security. You can find me on Twitter at jleitschuh and on GitHub under the same handle. A little bit of a disclaimer, everything available in this talk is available for free for open source. I'm also sponsored by GitHub. I'm legally obligated to say that. This work is sponsored and supported by the Dan Kaminsky Fellowship at Human Security. For those of you who don't know, Dan was a famous security researcher known for a famous vulnerability in DNS back in 2008. He's also known for his compassion and kindness in the security community, and unfortunately he passed away last year. And the Dan Kaminsky Fellowship was created to sponsor a fellow to work on a project that helps improve the security of the internet. And so that's the work that I've been doing for the past year here. So spoilers, we're going to jump ahead, to the punchline. So I generated over 150 pull requests to fix zip-slip across the open source ecosystem, primarily in the Java ecosystem. The story starts with a simple vulnerability. And this vulnerability was the use of HTTP to resolve dependencies in my corporate company's Gradle build. And I was curious how I had gotten this code into my build because there was a security vulnerability. And the answer to that question was that I had actually copied and pasted this snippet of code from an open source project that I was relying upon. Why is the use of HTTPS important? It's because if you're not using HTTPS to resolve your dependencies and you're not doing additional artifact integrity checking, it can result in your artifacts getting compromised by an attacker in the middle, by an attacker who's in the middle of your connection, and this can lead to the artifact that you're downloading, the jar file, or being compromised and have additional code injected into it that can compromise your CI/CD pipeline or your developer machine. And this is an example of that vulnerability existing in Maven POM files. So Maven is used to build 50% of all the Java ecosystem. Gradle is used to build the other 50% of the Java ecosystem. And Gradle is also used to build 99% of all Android apps. And so this vulnerability was everywhere. It existed in organizations like Spring, Apache, Red Hat, Kotlin, JetBrains, Jenkins, Gradle, the Groovy, Elasticsearch, Eclipse Foundation. So on top of that, Oracle was vulnerable, the National Security Agency, LinkedIn, Stripe. I found this in the open source projects of all these different organizations. And when I reached out to Maven Sonatype is the equivalent of NPM to the JavaScript ecosystem and pip for the Python ecosystem. When I reached out to Maven Sonatype, they said that 25% of their traffic was still using HTTP in June of 2019. And so I reached out to the major artifact servers in the Java ecosystem, Maven Central, JCenter, Spring, and the Gradle plugin portal, and pushed forward an initiative to decommission the use of HTTP in favor of HTTPS only for the entire Java ecosystem. And these organizations were willing to work with me, and they all published blog posts announcing the deprecation of the use of HTTP in favor of only supporting HTTPS to resolve dependencies. As you can imagine, however, in January of 2020, which was just days before we were planning on decommissioning this, the use of HTTP, Maven Sonatype looked at their traffic again and saw that 20% of their traffic was still using HTTP. And so you can imagine what might have happened on January 15th, 2020. Broken software. Lots of broken software, unfortunately. But we stopped the bleeding, and we fixed this glaring security vulnerability impacting the Java ecosystem. But what about the other repositories? Unlike pip and NPM, Java uses a lot of different repositories. Companies can run their own artifact servers. So this fixed it for the top most commonly used artifact servers. But what about the rest of the ecosystem? And I thought, why don't we just fix the code that's vulnerable? And so I was inspired by this idea of bulk pull request generation to fix these vulnerabilities across the entire ecosystem. So how? How did I do this? Well, to find the projects that are vulnerable, I used a CodeQL query. And CodeQL, you can use CodeQL to scan projects, the entire ecosystem of a language to find this vulnerability. And from that list, I was able to get a list of vulnerable projects. And for this CodeQL query, GitHub awarded me a $2,300 bug bounty for just contributing it back as a query that now any open source project or organization using GitHub Advanced Security is now consuming and will be able to alert for vulnerabilities against their infrastructure and their software. And then I wrote a pull request generator. The first version of it was a Python-based pull request generator. It was a wrapper over GitHub's Hub CLI, and it had one nasty regular expression and a lot of bouncing off of GitHub's rate limiter. And this is the code. There's an underlying engine behind here, but this is, the commit message and the regular expression required to make the fix. And to drill into the regular expression, the reason that I used a regular expression is because any XML parsers that you use in the industry, when they pull the file content into the parser, they lose all the formatting. And so if you make a modification in the parsed format and then dump it back out to a file, you'll make a massive diff to the file. And so regular expressions solve this problem by only letting you make a very narrowly focused change. However, the problem is if you use regular expressions to solve your problem, then you have two problems: the problem you originally had and the regular expression. And so regardless of that, it worked. I generated pull requests, 1,596 pull requests, and this is an example of the code, the diff that was generated. In total, I generated 1,596 pull requests to fix this vulnerability at scale, and this was done in 2020. As of today, there's about a 40% merge rate of those pull requests that were originally created. So, that's a significant number of open source projects now fixed that were previously vulnerable to this. And for this work, GitHub awarded me a $4,000 bounty thanks to the GitHub Security Lab. So I got hooked on this idea of bulk pull request generation. This is my contribution graph for 2020. You can see two major peaks where I actually had, engaged in these bulk pull request generation campaigns. So I have a problem as a security researcher. And the problem, I have ADHD, and that's not my problem. ADHD is not my problem, but I chase squirrels. I love finding vulnerabilities. And I love reading vulnerability disclosures. And the problem that I have is if I read through a vulnerability disclosure, I will usually be like, I wonder where else this vulnerability exists. And the tools that I have, like GitHub Code Search and CodeQL, allow me to find vulnerabilities at scale across open source. And the problem that I have is that I'm finding too many vulnerabilities. As an example, this is a result from lgtm.com, which is owned by GitHub. All the results of a CodeQL flagging down zip slip, which is a pretty critical security vulnerability, and we'll dive into more later. But there are pages and pages and pages of this that you can find. I need automation to fix these vulnerabilities at scale because I can't individually, as a reporter, report to all these individual projects that are vulnerable. There's just not enough of my time and enough of me to do that. And this is where OpenRewrite comes in. The underlying basis for OpenRewrite is that OpenRewrite extracts, while your compiler is running, your Java compiler or any other compiler, it extracts the abstract syntax tree from your code, and the abstract syntax tree is the thing that your compiler operates on to generate the bytecode or whatever you need. The problem with the abstract syntax tree is that the abstract syntax tree, if you were to dump the abstract syntax tree back out into source code, you would have no white space. All the comments would be lost, all the additional context would be lost, and so you can't make transformations of source code based just upon the AST. And so we need, what OpenRewrite offers and unlocks is a format preserving abstract syntax tree. All the comments are preserved, all the white space, all the tabs, all of that information about the source code is preserved, but in an abstract syntax tree that you can manipulate and make changes to and then dump back out into source code. OpenRewrite, while it's parsing your source code, also extracts information from your source code, like, does this project use tabs? Does this project use spaces? Do they put braces on a new line? And so new code can get generated looking like the surrounding code, which is really important because you want to make sure that when you're generating code, it looks like the code that the maintainers created, so that you're not getting complaints of, this doesn't match the formatting of the code. Thanks for the contribution, but we can't accept it. And on top of the preserving the style, OpenRewrite is also a fully type attributed AST. So this is an example of this log statement. Is that log for J? Is that SLF for J? Is that log back? You might need to know that to make a transformation to fix a vulnerability or fix something in your code. I can't imagine there ever being a security vulnerability in a massive logging framework used by the entire industry. log4j. So, that's why this stuff is important. And OpenRewrite, the AST is both syntactically and semantically aware. You can see that with all this information, with all the type information and all the spaces, you end up with a much more rich graph. There's actually 6,000 nodes missing from this graph on the right, because if we were to add them, it would be too dense for you to actually be able to see anything meaningful. And then when you want to generate new code, you need to generate an AST to insert into the existing AST when you're making these transformations, because even simple code that you're trying to change produces complex ASTs. Let's assume that we need to inject this little bit of code to fix the vulnerability zip slip, which we're going to talk more about later. OpenRewrite comes with a templating engine to generate an AST for your code to let you insert it into a specific location in your source code to make transformations. And it also comes with a coordinate system that lets you specifically place it at a specific coordinate, and that lets you target specifically the changes that you need to make to fix a vulnerability or fix whatever you need in your source code. And so that lets us inject this fix into the AST in a way that matches the formatting and styling of the surrounding source code. And so what's possible now? What other vulnerabilities can we fix with the unlock that OpenRewrite provides? As part of my research, I looked at 3 different vulnerabilities: temp directory hijacking, partial path traversal, and zip slip. Unfortunately, given the time that I have, I'm only going to have the time to cover 2, so we're going to jump right into partial path traversal and zip slip. The first vulnerability that we're going to talk about is partial path traversal. Partial path traversal, let's assume that you have logic that you want to sandbox to a single directory or a user, let's say user/sam. And you have another user local on that system, and you have user/Samantha. Partial path traversal allows an attacker to access a sibling directory with the same prefix. This vulnerability exists because you've incorrectly sandboxed your logic to user Sam, but you haven't adequately protected against access to sibling directories with the same prefix, like user Samantha, because user Sam is the same prefix as user Samantha. And so this is the vulnerability for partial path traversal. And the reason this vulnerability exists is when you're calling getCanonicalPath on a file, getCanonicalPath normalizes the file to remove path traversal, like .. sort of payloads that may be supplied by a user. And but the problem with getCanonicalPath is that when you are working with a new file and you supply a string that has a trailing slash, when you call getCanonicalPath on it, you end up with a string that does not have that trailing slash on it. And so when you do a starts with comparison on it, it allows for bypass. So as an example, let's assume that you've got user Sam as the directory that you're trying to sandbox to, and you have user supplied input that comes in that's path traversal payload. When this gets appended together and gets normalized by getCanonicalPath, you'll see that this starts with clause is no longer valid, and this IO exception does not get thrown, even though this is breaking out of this logic that this guard is intended to protect against. So the fix for this is to simply re-add the file separator on the end of the path. However, that's less than ideal because you're still comparing strings. The better solution is to use the Java path object to compare strings. The starts with method for that does the correct comparison in a way that's guaranteed to be safe. So how do we find this vulnerability? We need to look for subjects and arguments that our getCanonicalPath. And from there, we also want to look for cases and make sure that that path separator is not being appended, because something critical about this is we don't want to fix vulnerabilities that are not present, because if you do that, you're going to end up just upsetting maintainers, you're going to waste time, you want to make sure that you're not doing that. So you want to only fix vulnerabilities that are really truly vulnerabilities. It can't just be that easy though, right? Just those two things. Well, developers write code in a lot of different ways. Let's say that a developer, instead of putting everything as one line, they instead extracted one of those components into a variable. Or they extract the argument into a variable. Or they have the fix specified in a variable. How do you determine whether or not that's vulnerable or not? We need this new concept, and this concept is called data flow analysis. Now, data flow analysis allows us to track through the code that there is a variable flowing to this if check, and also lets us, we can do multiple bits of data flow to track logic in multiple places in our source code. But it also lets us track through intermediate variables, so it can be really powerful to allow us to determine a vulnerability's presence or not. Dataflow allows us to uncover hard-to-find vulnerabilities and prevents false positives. The Dataflow API is very similar to CodeQL's Dataflow API. So if you're familiar with writing CodeQL, I wrote the API to let you translate that knowledge very easily between CodeQL and OpenRewrite. Also let me translate my knowledge much easier. And so putting it all together, this is an example of the fix for partial path traversal. You can see the change made to fix the code to use the correct starts with call. So the second vulnerability that I'm going to discuss with you all is a vulnerability called zip slip. So zip slip is a path traversal vulnerability that exists while unpacking zip file entries. So let's assume that you're being supplied a potentially malicious, untrusted zip file, and you're unpacking that into a directory as a software, in your code. Zip slip, the vulnerability allows a malicious zip file to unpack its contents into destination directories unintended by the original author of the code. So you may specify a destination directory, but because the zip entry, which is zips are basically entries to contents of the file. If the entry is a path traversal payload, when it's appended to the destination directory, you can escape that directory, and that can lead to remote code execution and overwriting other sensitive files on the system, leading to compromise of the system at large. And so this is the zip slip vulnerability in Java. And the vulnerability exists because the entry is being trusted to be used to create a file object, and then that file is being written out to when the file output stream is created. If that was outside of the destination directory because of a path traversal payload, bin.sh, you could overwrite the contents of that bin.sh to allow for, next time someone loads up the shell, run arbitrary code. Zip slip is complicated from a fixing perspective, and the reason that it's complicated is because while this is a valid fix for this vulnerability, where you have this guard prior to the unpacking logic, there's also another valid fix. And the other valid fix is this, where you put the logic inside of an if check. And so how do we know between these two if there's not a vulnerability or if there is a vulnerability? Because both of these are valid fixes for this. Again, we don't want to fix non-vulnerable code because we're just wasting time. We're going to upset maintainers. So we need this new concept called control flow analysis. Control flow analysis allows us to differentiate between vulnerable code and non-vulnerable code. Control flow analysis and control flow is a graph representing the steps of a program and how it flows, and there are these concepts called basic blocks. Basic blocks are the set of contiguous operations that are going to occur in a program without a jump. And then there are branches where the logic will fork, and that's where you have conditional nodes in the graph. And so we can walk this graph to determine if a vulnerability is present or not based upon looking for places in the graph where conditional nodes occur and walking branches of that graph to determine what operations will be actually reachable. So we can determine for this bit of code what the control flow graph is and see that there is a control flow node that guards correctly against this unpacked logic, and that because of this guard, it's not vulnerable. And so when we put all this together, we can generate a fix that is only fixing vulnerable code and not fixing non-vulnerable code. Additionally, this fix can be even more complicated based upon the surrounding code and unpack variables and move them around because of the power that OpenRewrite provides us. And so let's talk about pull request generation. If you got a security vulnerability, everybody gets a pull request. So there's a problem with pull request generation. And one of the major problems with pull request generation is how fast we can generate pull requests. In order to generate a pull request, I know that a lot of you are GitHub users and Git users. The steps required to generate pull requests are as follows. First, you need to check out the code, download the source code repository, and then you need to branch to make your changes on a branch of the Git repository. And then you want to fork your repository on GitHub. And then you need to rename the repository on GitHub the fork that you've made. And the reason that's important is because if you don't rename the repository, when you're generating tens, hundreds, or thousands of pull requests, you're going to end up with name conflicts. And so you need to rename each repository to something that's going to be unique so that you don't end up with those name conflicts. And then you want to push your changes and then create a pull request on GitHub. And three of these things, forking the repository, renaming the repository, and creating the pull request on GitHub, are GitHub API calls. And each GitHub API call, according to the documentation, requires that you wait at least 1 second per operation per user. And on top of that, they also have secondary and tertiary rate limits that are limited documentation. One of them is not documented at all, which basically says back off completely and just wait some X period of time that's not really defined. So keeping those things in mind, the answer is basically just slow down and stop. You generate pull requests at a much slower pace than you'd really think you'd want to. And so if there's anybody from GitHub watching this talk, if you could stop rate limiting your API, or at least reduce it a bit, it would make my life a lot easier as a security researcher. So we made it this far. The vulnerability's been detected. We've detected the style, so we can generate code looking like the surrounding style. The code has been fixed, and a diff has been generated, and the rate limit has been bypassed. How do we actually do this for all the repositories across open source? So at this point, I want to introduce you to Moderne. Moderne is free for open source projects. They index over 7,000 open source projects, and it lets you run OpenRewrite transformations at scale. And it lets you generate and update pull requests, all the pull requests you're generating. Moderne is the parent company maintaining OpenRewrite. And there are over 800 recipes that have been developed to fix vulnerabilities, perform framework migrations like migrating from JUnit 4 to JUnit 5, Spring or older versions of Spring to newer versions of Spring. And then also for security research, it lets me automate the generation of pull requests to fix these vulnerabilities at scale across open source. So when I've identified the vulnerable projects, I can run the recipe against all these projects and generate a diff. And from that diff, I can select all those projects and say I want to generate a pull request for these things. And so I can say that I want to specify the commit message, the commit title, the pull request title, the branch that I want to generate the pull request against, the organization that I want the pull request to come from. I can supply my GPG key and the private key and then generate pull requests from my account as if they're coming from me. And they are coming from me because I wrote the recipe that actually generates the fix. But there are more than just 7,000 open source repositories in the world. How do we find the vulnerability that we wanted so we can generate the fix? And that's where CodeQL comes in. CodeQL scans, as I said earlier, 100,000 open source projects and 35,000 open source Java projects. And so I can write a CodeQL query to find the vulnerable projects. And then given that list of vulnerable projects, I can give that list back to Moderne as an open source pull request to a CSV file, and they will then ingest those list of projects that I need them to be aware of into their SaaS so that I can run my recipes against those projects as well. So finally, let's go generate some open source pull requests. And I did. That's what I did. I generated pull requests. I've generated quite a few pull requests in my career. Just covering the 3 projects that I've been engaged in for this work under the Dan Kaminsky Fellowship, I generated 64 pull requests to fix temporary directory hijacking, 50 for partial path traversal, and 150 for zip slip. I've actually generated over 600 new pull requests in 2020 as a part of this work. And to my name, I've personally been involved in generating over 5,200 pull requests across the open source ecosystem to fix a variety of different security vulnerabilities. And this is an example for this particular campaign of one unlucky project that was the recipient of all three of my pull requests for all 3 vulnerabilities that I was looking at this year. And this is my contribution graph for 2022. You can see the campaigns that I've engaged in, and I have more work ahead of me that I'm planning on engaging in to fix more vulnerabilities as the year proceeds. So now let's talk about some best practices for bulk pull request generation. The first thing is messaging. As a security researcher, you're reaching out to a maintainer with a vulnerability, and maintainers are currently pretty familiar with receiving bug reports, but security vulnerabilities are more sensitive, and they have risk associated with them. So you need to be conscious of that. And you need to communicate that in a way that respects the maintainer and the project for the code you're fixing. And so I include details like the impact of the vulnerability, how the vulnerability can be exploited, and why the fix is written the way it is. There's a saying out there, all software problems are people problems in disguise, and this is very true in this case, right? I'm throwing a technical solution at a human problem, but you do need to consider and make sure that you're aware that there is a human and a maintainer in this loop, that you need to be conscious of that as a security researcher. And so here are some more just kind of other lessons that I've learned. First off, sign off on all your commits. This is what the git commit sign off looks like. It's just a line in your commit. And you might ask, why do I need to sign off on my commits? And there's a bunch of lawsuits that occurred several years ago, TLDR lawyers. If you don't, you might get your pull request rejected by evil dragon bureaucrats. Lesson 2, be a good commitizen. GPG sign your commits. This is what GPG sign commits look like. They're verified. Otherwise, you might get impersonated like Linus Torvald has been a couple of times, unfortunately. Then CCOM. CCOM is a commit format. If you're interested in a commit format specifically for security fixes, this might be something that's good to look into. I don't have the time to go into it now, but it's something to look into. Lesson 4, there are risks of using your personal GitHub account. For those of you who have used GitHub for a long time, are you familiar with the angry unicorn? Unfortunately, this is what you get when something goes wrong on GitHub. And this was my GitHub profile for most of 2020. So there are risks. You might break your GitHub account. They might have fixed this, but I still recommend using your personal GitHub account for this work because it helps the maintainer recognize that it's coming from a real person and not a bot or an organization. That human element is important in this work. Lesson number 5, coordinate with GitHub. Before you attempt this sort of work, reach out to GitHub, let their security lab know. This will keep you from getting banned, or at least keep them aware of what you're doing. They want to talk to you about the work you're doing, so I did that, and I highly recommend that you do that too if you want to engage in this work. And then lesson 6, consider the implications of this work. When I engaged the first time in this campaign of fixing this vulnerability, I got this issue. Is this responsible disclosure? And I don't use the term responsible disclosure, I use the more nuanced term coordinated disclosure. But regardless of the term, the answer is no. This is full disclosure of a security vulnerability in open source without a fix. You're dang a maintainer. And so there is something to consider about this work and the risks associated with that because you are publicly exposing a maintainer and the project to risk by identifying and fixing this vulnerability. So, in conclusion, as security researchers, I believe we have an obligation to society. We know these vulnerabilities are out there. There's the statistic that GitHub provided back in 2020. For every 500 developers, you'll only have one security researcher. We as security researchers are heavily outnumbered, and there are more vulnerabilities than we can possibly dig out. But here's the thing. As security researchers, we've seen these same vulnerabilities again and again and again in pen test reports, in bug reports. We as security researchers are aware of these vulnerabilities. Spoiler, a lot of developers don't watch security conferences. Some of them do. And for those people, I have a lot of respect. And I have a lot of respect for a lot of developers, regardless. But we have to, as security researchers, meet the maintainers where they are. And we are heavily outnumbered. And so I believe that bulk pull request generation and automating our security research is some of the best way to scale our knowledge of math, science, technology, and security to have the highest impact that we can as researchers. And with that, I want to leave you with one final quote. This is from Dan Kaminsky. It's on his Twitter profile, and it's still there to this day. We can fix it. We have the technology. Okay, we need to create the technology. All right, the policy guys are mucking with the technology. Relax. We're on it. And so some closing notes. Learn CodeQL. It's a really incredible, powerful language. And contribute to OpenRewrite. You can deploy your security fixes or other fixes that aren't even security related at all at scale. Then join the GitHub Security Lab and OpenRewrite Slack channels. And if you want to get involved in open source security research or open source security in general, consider joining and participating in the Open Source Security Foundation. There are meetings happening on a weekly basis, and there's an open calendar. You're welcome to join any of the meetings. Finally, I want to leave some thanks. Human, my employer, for sponsoring the Dan Kaminsky Fellowship, Moderne for working with me, Lydia Giuliano, the speaker coach that I worked with, and Sham, my intern, who came up with some of the graphics that you saw in this presentation. So, thank you.